right, so now we're going to talk about how to basically approximate a derivative. So considering the similar example to what we did with the cyclist, so suppose someone is driving their car and the distance in miles they travel over time in seconds is shown in the graph of f of x. So we want to figure out exactly how fast they were traveling, aka your instantaneous rate, at our time x equals 1. And so what we can do is we can approximate the instantaneous rate by finding our average rate of change from 1 to 4 seconds. So if I start here, there's my 1, here's 4. So if I find the slope, let's see if I can do it. Oh gosh. I wonder if I have a way to do a straight line. Aha, from here. It would work if it was not a white line. There we go, from here to here. So we're finding the rate or the slope of that line, which is the average rate of change from 1 to 4 seconds. So we're basically finding f of 4 minus f of 1 over 4 minus 1. Okay, and so you can either tell from the graph or you can tell because we have the equation down here. If I plug in 4 squared is 16. So I get 16 minus f of 1, just 1, over 4 minus 1, which is 3. So I get 15 over 3, which is a nice 5. And again, making sure you're using the units correctly. So distance in miles, it would be 15 miles over 3 seconds. So 5 miles per second. Wow, you're flying. Okay, so that is an estimation for the exact speed we're going at 1. But I'm using the average speed from 1 to 4. So now an even better approximation would be if I found the average rate of change from 1 to 3 seconds. So I'll do that in a different color. So if I'm finding the average rate of change from 1 to 3 seconds, so I'd be finding the slope of that line. Okay, so f of 3 minus f of 1 all over 3 minus 1. So it'd be 9 minus 1 over 2. 8 miles for every 2 seconds, so 4 miles per second. Okay, so that's a better estimation. Remember, we're trying to get closer and closer to the exact slope at that one point on that line. So we're just moving our points that we're finding our average rate of change for closer and closer to that point. So now let's do 1 to 2 seconds. 1 to 2 seconds. I'm finding that's almost a tangent line there, almost. So we're getting better and better estimations. So f of 2 minus f of 1 all over 2 minus 1, which would give me 4 minus 1 over 1, which gives me 3 miles for every 1 second. So 3 miles per second. Okay. If we got really close to 1, so for example, the average rate of change from 1 to like 1.1 seconds, like this was 1 to 2, this was 1 to 3, this is 1 to 4. So if I got a really close to 1 to 1.1, the approximation would be even better. So let's say we pick some arbitrary value really close to 1. So like, for example, 1 plus some value h. Right? And I'll make that h really small. So it can be like, here it would be like 0.1, or I can make it 1.001 or 1.0001. So we'll call it 1 plus h. If I wanted to find the average rate of change to from 1 to 1 plus h seconds, what would that look like? Well, that would look like if I did, right? Here's my point, technically. I'm 1, oops. It would be 1 plus h. Where am I trying to write this? So if this is my x value, right, then my y value would be 1 plus h comma f of 1 plus h, right? Regardless of what that h value was. And we're picking an h value that's really, really small, because then I'll have this point will be really, really close to 1, and it'll be a really good approximation. So if I wanted to find the average rate of change from 1 to 1 plus h seconds, what would that look like? Well, I'd take my y2, so f of 1 plus h minus f of 1. Same way that I was doing it up here, right? F of 2 minus f of 1. So f of some value really close to 1 minus f of 1 all over 1 plus h minus 1. Then that would simplify a little bit, right? I don't actually know what this value is, 1 plus h. And then I'm going to leave it as f of 1. 1 plus h minus 1 would be h. If we wanted to find the instantaneous rate of change at 1, it would be really good if this number was really small. You see how it kept getting smaller? So it was 3 and then 2 and then 1. What value would I like this to approach, but never to actually equal? Hopefully, you said 0, right? If I make my h value super, super small, then I would get really, really close to 1, and so I would get a really good secant line. It would basically be a tangent line. But I can't have h actually equal 0. So in mathematics, how do we notate h approaching 0 mathematically? How we've learned about something that helps us approach a value without actually equaling that value. We use a limit. So we would like the limit of h approaching 0. Okay, and then you want it to apply to that function, the 1 plus h minus f of 1 over h. Awesome. Our big idea that comes from this is basically the instantaneous rate of change of a function at a point can be expressed by this limit. So basically you're doing your limit of your y2 value, and I'm going to use x in this scenario because we're not always necessarily approaching 1. You could be approaching 2 or 3 or 4, or excuse me, we're not always finding the instantaneous rate at 1. Like I could look for the instantaneous rate at 4 as well. So we'll just call that x. So f of x plus h minus f of x over h. And we want that h to approach 0, because then these two y values would get really, really close to each other, and the x values would get really close as well. An alternative form of that definition is the limit of f of x minus f of a all over x minus a. And that basically means that you want your x value to approach a, provided that the limit exists. These are common forms of the definition of our derivative. This one's the most standard one, and this one's often referred to as the alternate form. And I'm just going to kind of show you visually what that means, right? So if down here, if I had x and then I had x plus h, that means that the distance between them would be h, right? And then this is f of x, and then this is f of x plus h. And so basically what I'm saying is I want this h to get increasingly small. I want it to approach 0 because I want this point to get really, really, really close to this one, so that way I can find the slope of the tangent line there instead of always just finding the average using the slope of the secant line. Okay, so that's basically how that definition works. The alternative form is if I had x and then I had a, right? Yeah, okay. I suppose I should flip them around here, right? Yes, correct, sorry. A and then x, and then f of a and f of x. It's basically saying the same thing, right? So I basically want my x value to get really close to my a value because I want this point to get really close to this one, so that way when I find my quote average rate of change, it gets closer and closer to actually finding my instantaneous rate of change, aka the slope of my secant line. So with all of these things, I'm trying to find, if this is the point, I'm trying to find the exact slope at that point. right? I want to find that exact piece right there. I don't want to settle for average between 2 points. I want to find the actual slope at that point, okay? So that is basically where a derivative comes from, is using that limit. Some of the notation pieces for this. So y prime is this little like apostrophe that's up there. This means derivative. It means the derivative of the function y. So it's the instantaneous rate of change of your function y. You can also see dy dx, which is how you pronounce it, and this is the derivative of the function y with respect to x. F prime of x is the derivative of f with respect to x, and so you'll see f prime is probably going to be used most commonly, and then dy dx would be used next. You could also say df dx, which is the derivative of your function f with respect to x, or ddx of f of x. So you're saying I'm taking the derivative of this function with respect to x. Those are all different ways that you could imply the derivative, okay? And so what we're going to do next is we're going to practice using our definition of the derivative, our limit notation definition of the derivative, to find instantaneous rates of given functions. And it's a really cool thing to be able to do because you can only do it with calculus. Awesome. So that's what we'll move on to next.